today's talk is about contaminants, which is really, we're trying to justify why we're treating water. Okay, so like what's the problem that we're dealing with? And hence why is this class really important? Drinking water contaminants. Okay, so let's go. So I'll talk a little bit about history. I really enjoy history because it gives you a sense of what we have been assuming as we've been developing our understandings. And I feel like by studying a little bit of history, you can more easily understand that what we think we know now might not actually be right, because you can look back in history and see people who were dead certain about many, many things. And then you can look back and you can say, oh, but they should have known that wasn't right. So a reading of history on any subject is worth a lot. So a little bit of history on our understanding of waterborne disease, and then some on drinking water standards. So just a few like important dates. And it gives you a sense of like how things happened and how developments in water treatment didn't like follow some nice logical progression. Like it wasn't that we first figured out that there were germs, there were disease-bearing organisms in water, and then we decided that we were going to try to remove those pathogens. No, we like had this sense that water was somehow dirty, and so whatever that meant. And so the first low sand filter, the first sand filter, was used to treat some of London's water back in 1829, which is pre-germ theory. 1850, John Snow established the link between drinking water from a contaminated well and cholera. So there's the famous case where John Snow did a little bit of epidemiology, figured out who was getting sick and dying, realized that they were all in this neighborhood or mostly in this neighborhood, concluded that it was the thing that they all had in common was drinking from this well, and ended up removing the pump handle to take that well out of service. And that was a really cool engineering act to prevent people from using a really contaminated water source. And that was also before germ theory was well understood. Here in the United States, Poughkeepsie, New York installs the first filter. And where's Poughkeepsie? Okay, you guys are from Ohio, you're not from New York State, so that's not fair. Do I have this right? I think I have Poughkeepsie as being south of Albany. And that's the story. It was south of Albany. Check me out on Google Maps and see if I got this right, but it's south of Albany. And so it was getting Albany's untreated wastewater in the Hudson River and was using that as its water source. And so things weren't going well for folks in Poughkeepsie. There was a lot of people getting sick and dying. And so they installed a filter. And then a few years later, we finally realized that, oh yeah, these sand filters amazingly are removing bacteria. And we'll talk about filters, weeks down the road. But one of the amazing things is if you look at a filter and look how it's made and look at how big the pores are inside the filter, the idea that it removes bacteria makes absolutely no sense. So this is a wonderful case where people invented a solution that solved the problem, where if they had known what the problem was, they would have thought their solution didn't make any sense. But happily, they didn't know what the problem was that they were trying to solve, and they tried something that worked. Just amazing. Okay, and then there's this case of a cholera outbreak in Hamburg, Germany. I'll come to that in a little bit later. And I feel like you can't talk about the whole issue of essentially waterborne disease without talking about toilets. So toilets are these amazing devices that take perfectly clean, drinkable water and turn it into wastewater. So it's an engineering device that does exactly what we don't want anything to do. So you have clean water in, dirty water out. But they did this amazing thing where they made cities habitable. They removed human waste from cities by connecting, assuming that you had a sewer that you could tie these to. That meant that the water that you used to flush the toilet carried the waste down the sewer, and that meant that there wasn't so much human waste easily accessible in the city. And so that was a good thing right at that level of the city. Unfortunately, as it carried the waste away was too close in many cases. So those sewers, remember, this is before people were thinking about treatment. And so those sewers just went right to the local water body, whether it was the nearby river. So think about the Thames River in London, or it could have gone to a lake. And we'll talk about Chicago in a second. London drained its raw sewage into and withdrew its drinking water out of the Thames River. So you can imagine that creates a bit of a problem, and I'll show a lovely graphic of that in a second. So first, the case of Chicago. So here's Chicago, and there's Lake Michigan. And what Chicago did is it was dumping its sewage into the lake, and it was also bringing its water out of the lake. And so it had a closed system, and that kind of worked because Lake Michigan is huge, but not a good idea. And if the currents go wrong, you could imagine some of your wastewater getting right into your intake for your drinking water plant. And except there was no drinking water plant, it just was into the city. And so that was no good. And I love this solution. You know what the folks, the engineers in Chicago figured out? They looked at this problem and they're like, okay, the problem is that our sewage is ending up in the lake, and that's our drinking water. So if the sewage didn't end up in the lake, that would solve our problem. How could we make this so that the sewage doesn't end up in our lake? And they came up with a very clever idea that if you just go about 20 miles and just a few feet up in elevation, you end up in the Mississippi watershed. And so all they had to do was lift their wastewater a tiny bit, get it over that tiny ridge, and all their wastewater goes down to Mississippi instead of into Lake Michigan, and their problem is solved. And you should be, as Michael is, kind of hanging his head in shame, realizing, oh, great, that solved the problem for Chicago, but there are just a few cities and towns downstream on the Mississippi that aren't going to be so happy with that solution. But that's what happened. Go back to London. So there they were dumping their wastewater into the Thames and taking their wastewater, their drinking water out. And so I love this quote: "A portion of the inhabitants of the metropolis are made to consume in some form or another a portion of their own excrement, and moreover, to pay for the privilege." So there was some unhappy writing about this situation, and there was a wish for, there ought to be a better solution than this. So here's a cartoon about that, and I just want to highlight, okay, so this is, you can see the kind of the black streams, which are representing sewage getting dumped into the Thames River, and then Neptune is sitting on the intake for the water supply and showing all this excrement coming into that water supply. And I know that the image is not great, but you can make out maybe a few of the sayings, like it's devilish thick and it makes me sick. And there's a line about give us clean water. And there's a line about sewer. Why, there are 130 such. There are 130 sewer outfalls coming into the Thames River. And why do you drink that? So London had a different problem, and they had to send their sewage somewhere. And so it's interesting, London, the engineers in England worked at both figuring out how to treat their wastewater and how to treat the drinking water. So instead of adopting the Chicago approach, they worked on treatment at both ends. Here's another really interesting case. This is the case of Hamburg, Germany, and a large outbreak of cholera with 8,600 people dying. So this is a major, major event in 1892. And what's interesting is you see here the Elbe River flowing right to left, and you see that Hamburg has some of their sewer outfalls upstream of Altoona. And just like Poughkeepsie started treating their drinking water because they were getting Hudson River water that was contaminated from Albany upstream, same thing happened here, where Altoona, they kind of had this sense that, oh, this isn't good, we got to treat this water. And so Altoona has sand filter beds that they're using to treat the water because they realize that they're drinking the excrement from Hamburg. So they treat their water. And then Hamburg has this really nasty cholera outbreak. And cholera makes you sick, makes your digestive system go to town. You produce tons of cholera in your excrement. And so that was going down to sewers and down the Elbe towards Altoona's intake. And yet the folks in Altoona didn't get sick. And that's like, oh, that's interesting. If we understand how the water was flowing and where the intakes were located, Altoona should have been hit really, really hard. And so apparently their filters saved them. And if we look in more detail, this is looking at the boundary between Altoona and Hamburg, and the filled in dots are cholera cases, and the open dots are cases in Altoona where they drank water in Hamburg or they worked in Hamburg, and so they drank water there. And so you see that this political division really matches where people were getting sick, and all the evidence points to it was actually the water supply on the Hamburg side because the pipes stopped at the political border. So the conclusions from this is that cholera was waterborne and that they were using slow sand filters, and that slow sand filters may have, I'll be careful, I won't say it did because we don't know for sure, but slow sand filtration may have protected Altoona. So just very interesting. So some contaminants you might be thinking about is, oh, you're not really a fan of having cholera in your drinking water. Now you're realizing, oh, there's this fecal oral pathway. So people who get infected with these waterborne diseases then have excrement that's loaded with those pathogens. And so we want to break this fecal oral pathway. And this is showing there are tons of ways that you can go from human excrement. It could contaminate the groundwater, it could contaminate the surface water, it could end up on the land and contaminate the soil or be indeed picked up by crops that are planted in the soil. And so if you didn't wash the crops before you ate them, you could end up having pathogens on those crops. And so you'd have a path for ingesting some of those pathogens. There's so many paths, and then the question is, well, which are the paths that you have to worry about most? And of course, you should worry a little bit about all of them. It makes it clear that washing your hands, which I'm sorry to report, can be a direct fecal oral pathway, okay? So washing your hands is really, really important. And obviously the water that you drink is important. And basically anything that you put in your mouth ends up being of concern because you're trying to break that loop. So I get really excited about hand washing. I think that hand washing is actually one of the key things for public health. Yeah, I'll go down that path here. What device in your home or your dorm makes it easy for you to wash your hands? You know, we talked about the toilet, but the other critical infrastructure is the sink. And if I could, like, you know, flash my magic wand and make things happen, I would want everyone on the planet to have a functional sink in their home, a place where they and where their children who are 4 years old can easily wash their hands. And there's interesting studies about how people, how the amount of typhoid in the United States dropped off over time. And that's a whole other conversation. But it took a long time for typhoid to go away. And my favorite hypothesis is that the reason it took a long time is because it was correlated with when indoor plumbing and sinks got installed so that people could actually wash their hands. That's hypothesis. I don't have any proof. We can't go back and actually rerun that experiment. But I hope you come away thinking that maybe washing your hands is important. Okay, so let's take this. Here's an interesting opportunity. It's a really cool device that's called the Life Straw. This is current technology. I don't know, it's a number of years old. It's been out there for a while, and it can be a way to deliver safe water to people where they don't have access to safe water. And I would like you, and man, I could send you into breakout rooms, but I think let's not. You could just look at this and ponder for a second, but I'd like to hear from a couple of you after a minute. What do you think are potential fecal oral pathways for this device? So think about it. You have to be like a real critical engineer and think about, how does the user actually use this? What are the steps, and where are the potential fecal oral pathways, and how do you make sure that you break them? So think about an individual who's somewhere where there is no safe water anywhere. The only water available is contaminated water. What are they going to do? How are they going to use this device? And what do you see as potential pathways for still getting sick, even though you're drinking water that was absolutely safe? I'll give you a few seconds and then take a couple responses.
I would say like people's bacteria could get on the cap and then get transferred to where you put your mouth on the top.
Yeah, so you've got to grab a hold of that cap with your hands. And okay, let's go back one step further. Where was this device before you started using it?
Probably like in some sort of wrapper or box.
Yeah, the first time. And the second time?
It was used by someone else, probably.
Well, no, it's your personal one. We'll be nice. We'll make it be your personal one.
So like maybe a bag or a pocket.
Yeah, or maybe I'm mistaken, but I feel like I've seen pictures of these like hanging on a lanyard around the neck. So supposing that's the case, supposing this is on a lanyard. Matter of fact, they have the little hooks there at the top to hang a string on it. So you're carrying it, or it's. Now, what are some additional pathways? And Isaac doesn't have to answer all of them. Feel free to jump in, someone else, or Isaac is allowed to continue.
Could there be like aerial contaminants?
Absolutely. Yeah. So if you look at this environment, it looks like it could well be a dusty environment. And it's entirely possible for pathogens to be kicked up in the dust and be airborne and land on the device that you're about to stick your mouth around. Okay, and then where does your mouth go? Right on that top. And where was that top previously? It was just hanging around. So like a flaw in the design of this device is that the place where you stick your mouth isn't actually protected. Yes, they have a little cap for the very top, but they didn't think about where your lips go. Your lips are going to go down even further than that. And so if they were being really careful, you'd need a bigger lid that completely covers where your lips are going to go. And you see this lovely picture of a child drinking from water that looks quite turbid. It's cloudy. It's cloudy because there are particles in that water that are reflecting light or refracting light, one of the two. So what's going to happen as you're drinking that kind of water? By mass conservation, those particles end up in the filter, and that filter is going to start being more and more difficult to pull water through because those particles are going to add to resistance. I've never used a life straw, so I can't comment further, but I just know that if you're drinking really, really dirty water, you're going to have problems. I think there are methods to kind of rinse these filters, but it's a messy solution. But if you don't have a water treatment plant, this might be the best thing you have. So there's that. Okay, let's talk about standards. So we've got fecal matter in water that we would like to drink. And now we're like, okay, what are the drinking water standards that we want to have to make sure that the water is actually being treated properly and is safe to drink? And this ends up being a question about what would you like to have in your water? So there's a couple things that could be going wrong with things that are in the water. There could be infectious diseases. So there could be disease organisms, pathogens that are in the water. And there's a link there to bad bugs, which is on the wiki, the course wiki on GitHub. And there are many, many, many potentially infectious diseases that are potentially carried by water. So we would presumably like to not have many of those infectious organisms in the water. And then there's also non-infectious diseases. And this could either be acute or chronic. This is exposure to potentially chemicals, atrazine or other pesticides or other industrial chemicals that, or things like arsenic and fluoride, which are naturally occurring and also deadly. So they could be acute, where you drink a small amount today and that harms you significantly or even kills you. We would hope that one glass of water doesn't do you in. Chronic means that you're exposed to this over many, many days, over many months, maybe over many years, and it increases your probability of getting diseases, cancer or kidney damage or other harm to your body. So obviously we don't want acute things to be happening, and we would like the chronic to be at low enough levels that it's not a significant harm to almost everyone. Obviously, you would like it to be clean enough that there's no harm to anyone. It turns out that you can't actually go to zero harm. So you want to get it as low as like economically feasible. And this raises the question, how many pathogens do you want to have in your water? And man, I think that we should, because you're going to get tired of listening to me talk if I don't send you into a breakout room. So why don't you go into breakout rooms, and let's put 3 people in a breakout room and spend just really short, 2 minutes. So we're gonna start pulling you back out a minute from now, and I want you to discuss what you think the pathogen exposure ought to be. How many pathogens do you think should be in your water? Let's go for it. How many pathogens do you think should be in the water? Oh no, did Brendan end up by himself? No, he's fine, he's fine. All is good. Okay, now we give them 1 minute and then we send, can be really good for our immune system. So I don't have the definitive answer on this, but my vote is going to be for as low a level of pathogens as I can, hopefully, as I can like economically get to. And I'm not too worried about my immune system. My immune system, I can do fine by getting outside and playing outside sometimes, and I don't need to ingest pathogens. Okay, so let's actually go to what does the Environmental Protection Agency specify? So EPA, and this is like ancient history, but it's still part of what we're working off of. Is Safe Drinking Water Act 1974. It specifies both primary and secondary standards. Primary is all about things that are mandatory, that are health-based requirements. Secondary is suggested. They are non-health-based standards. And it's applicable to all water supplies serving more than 25 people. There's a similar set of like standards that are recommended by the World Health Organization. So they have drinking water quality guidelines, and I've linked to them here, and they're also linked off of the website. Primary standards for the Environmental Protection Agency includes these 6 classes: microorganisms, disinfectant byproducts or disinfectants, disinfectants, and then another one, disinfectant byproducts. So when you use a disinfectant, you get some unhelpful reactions with organic matter that's in the water, and those byproducts can be harmful. Inorganic and organic chemicals and radionuclides. So you look at that list, you're like, well, what about dirt? Like I've showed you some pictures of really dirty rivers, and dirt isn't on there. And it's interesting, the way we've categorized things, dirt doesn't show up here, it'll show up later. And I'll get to that eventually. Okay, so let's look at a few of these inorganic chemicals. I wanna highlight arsenic and fluoride. Many of these chemicals are present in the environment at various levels, depending on what the geology is. Arsenic and fluoride are strongly dependent on what the geology is. And there are places on the planet like Bangladesh and parts of India, and there are also some places in Africa where, and matter of fact, in New Hampshire and other places in the United States where there are high arsenic levels in the groundwater naturally occurring. And arsenic is nasty. You drink a little bit of it, it's not going to hurt you, but you drink it for a long period of time, it's going to build up, and so there's this chronic effect. Fluoride, you think of fluoride as something that is good because you've got it in your toothpaste, and the dentist says you should have it, and your water treatment plant most likely adds fluoride to the water, but it's here as a primary standard, as a health standard at 4 milligrams per liter. And it's because at 4 milligrams per liter and greater, there are negative health consequences. It makes your bones weak. It makes your teeth mottled and weak. And so a little bit is a good thing. A little bit more is a bad thing. And there are a number of places on the planet where there is naturally occurring fluoride in the groundwater that is at levels high enough that it's causing serious human health concerns. And both arsenic and fluoride are challenging to get out of water. And full disclosure, the course that I'm teaching here, I don't teach you how to get these out of water. It does turn out that the treatment methods that we're using for removing particles and pathogens would actually reduce arsenic and fluoride, but we have not developed a full treatment system and demonstrated that it works for groundwater. But flocculation, sedimentation, filtration is a classic approach for removing arsenic at the municipal scale. There are other chemicals on here that you don't want to drink, like lead. And the lead is not because it's coming out of the groundwater. The lead is there because it's in the pipes and it's being dissolved by the water in the pipes and being carried into the home. So that's why there's this huge effort now to remove lead pipes. And of course, you probably heard of the Flint, Michigan case, not because the water supply or the water utility was sending lead out from their treated water, but because they were dissolving the lead that was in the pipes. Here's a few organic. So we were an inorganic. So here's a few organic chemicals, and you may recognize a few of those. Some of those are industrial chemicals like vinyl chloride and toluene. There's PCBs, which were used for electrical transformers. There are a good number of agricultural chemicals like atrazine, alachlor, and there must be others. What's interesting is how many herbicides and pesticides are on this list, and you think about all the places where they are being applied, they get into groundwater, and agricultural communities, many farmsteads have their own wells, and so they're getting water from the ground that they've applied chemicals to, and so there's a very unfortunate cycle of agricultural communities being hit hard by these organic chemicals. So I can't teach you how to remove all these chemicals, but I want you to know that there are some great resources out there so that if you get a consulting job and they say, wait, community X has this contaminant Y, what are your best options for removing this contaminant? EPA has put together a very nice database, and I think I'm not going to click through this because you can do this easily on your own. The links are on the website, on the wiki course website, but it's very easy to click through, identify a contaminant, and then EPA provides a whole list of treatment options that can be used and some information about which ones are the best options. So that's a go-to database if you need to remove a crazy contaminant. Contaminants related to microorganisms. So here's some lovely organisms: Cryptosporidium, Giardia lamblia. I think I had a bout with Giardia when I was in Guatemala many years ago, and have no desire to repeat that experience. And MCLG stands for maximum contaminant level goal, and they've got 0. EPA would like there to not be any Cryptosporidium at all in the water that we drink, and the same for Giardia and Legionella and for enteric viruses. So that's the goal. So that's the goal that EPA sets, and I like those goals, especially because for Cryptosporidia and Giardia in particular, ingesting one is potentially enough to make you sick. So I would really not like to be exposed to any of them. And here's where turbidity shows up. So turbidity is not a microorganism, but that's where it shows up in the standards. And it shows up there because pathogens are particles, and whatever treatment technique that we use to remove lots of pathogens is going to have to remove those particles as well, because we're not going to just somehow pick out the pathogens and leave all the clay behind. So you have to remove all the particles. And then if you're removing all the particles, then having a really low turbidity means that there's a really low concentration of particles left, which means that you've knocked the pathogen level way down. So what's turbidity? Turbidity is a measure of the scattering of light by particles in a suspension. So when it's raining or when it's foggy and you can't see very far, you say it's cloudy. Same thing of looking at a suspension of particles in water, it looks cloudy. You can't see into it very far because the light is being reflected or refracted. And we talk about that as we call that dirty, which I like the use of that word. Like, yeah, it's dirty and it's not good. We would like to get that cleaned up. It's measured in NTU, nephelometric turbidity units, and that it's a Greek prefix there that stands for cloudy. The netphel is cloud in Greek. So it's a measure of scattering of light. So here's a very simple turbidity meter. So there's a light that's shining through a lens and into a sample. So here's my sample cell. And if there are particles in that sample cell, they might reflect or refract the light. And so the light, instead of going straight through, it gets bent actually in all directions. Some of it hits a detector that's at 90 degrees. And so if I see anything on that 90-degree detector, it means that there's some cloudiness, there's some particles in that suspension. And this is a really, really simple instrument. And one of my pet peeves is that they cost a lot of money. A portable one costs about $1,000. One that's inline costs $2,000 or $2,500. And yet what's in it is simpler than what's in your phone. And so one of my wishes is that these would be cheaper, because turbidity meters are like the first line of defense in verifying that your water treatment system is actually working. Because if you're not removing particles, then you're not protecting your customers from pathogens. So first step is getting the turbidity down. The guidelines for how turbid the water can be, isn't it interesting? Turbidity isn't directly in a primary standard. It's just kind of there as like a secondary thought. Like, it's not a microorganism, but it's listed in there as along with the microorganisms. And then it becomes like what we really focus on, in part because it is so easy to measure turbidity. It costs almost nothing as far as per sample. It's an easy test to run. Just put the sample in, take the measurement, press read on the instrument, or maybe it's reading continuously. So here's some guidelines. If you use conventional, and I love this word conventional filtration, conventional system, conventional means flocculation, sedimentation, and filtration. That's a conventional treatment system. And what that tells you is that what this course is about is like the most common treatment systems that are used on the planet: flocculation, sedimentation, filtration. So if you use conventional or direct filtration, which means that you just send the water right to a filter and you don't use flocculation and sedimentation first, the turbidity always has to be less than 1 NTU coming out of the filter, or and less than or equal to 0.3 NTU in at least 95% of the samples in any month. And then if you use a different treatment system, you have to follow state standards, and it has to always be less than 5 NTU. So if you have an alternate system for removing particles, EPA is willing to let you have dirtier water if there's you have to demonstrate that this is okay, but they're willing to provide an exception. Okay. And I'll just be cynical for a second. Like, how in the world did that exception get in there? Like, wouldn't you hypothesize that it was some actor that was fairly politically powerful to be able to get this exception that you can have slightly dirtier water for some other systems? Okay, and what I'm about to say, I don't actually know if this is true, but I would just wonder if it's not New York City. Because New York City doesn't filter their water for most of their water supply. And so their treatment is like settling in very massive and well-maintained reservoirs. And so that was their treatment system. And they wanted 5 NTU because their water does go above 1 NTU sometimes. I don't know if that's actually how this happened. That'd be a curious research project for someone to figure out, how did we get this 5 NTU in the standards? World Health Organization has similar standards. And then secondary standards, and just to point out, look, fluoride shows up again in the secondary standard, and this time it's not a contaminant level goal, it's like the goal. So now fluoride here is listed as 2. We would, hang on, I completely misspoke. These are also maximum levels. So that you don't want you want fluoride actually less than 2. For aesthetic reasons, you want color. So this is about the water looking like tea colored or yellow. You want that to be less than 15 color units, and there are devices for measuring the color of water. And you'd like the water to not smell bad. So there's a whole measure of how much odor does the water have, and you don't want it to have much odor. And notice that aluminum is there, and the levels that are set for aluminum are directly related to how soluble the aluminum is. And basically what they're saying is we don't want particulate aluminum in the water. We want just at least that it's dissolved. And I'll just go off on this for a second. There's a common notion that aluminum is a problem. And there was research a number of decades ago now, I believe, where they connected aluminum to Alzheimer's disease and other things. That has been pretty well debunked. And in any case, the water is a small part of our exposure to aluminum. And happily, aluminum is not soluble when it is at neutral pH. And so by the time the aluminum gets into our digestive tract where the pH is close to neutral again, even if you did eat aluminum, it's insoluble at that place. And so you're not going to be actually pulling much of it into your body. So our bodies are designed to handle the aluminum issue. Aluminum does end up being toxic if you're a fish and you live in an acidic lake. Then aluminum is toxic to the fish because they're no longer protected because aluminum is now soluble. If you could only afford one treatment process, what would you do? I want you to think about this because there are plenty of places on the planet where you can't do everything that you would like to do. And you have to come up with, okay, what's the next step? So if you lived in the town that had that water source and you had very limited resources, and you could only afford to do like the very first step in treating the water, what would you do? So I'm giving you the choices of, you could do flocculation and sedimentation. And I understand that this is completely unfair because I haven't taught you yet how all these systems work and what they do. So don't worry, you're not going to be graded on this. I'm just like, what's your initial opinion of this? You could do filtration, which, yeah, and you could do chlorination. Okay, so let's do this. I should have numbered these. Flocculation, sedimentation is 1, filtration is 2, and chlorination is 3. No, well, just doesn't matter. Let's just do votes. Let's use show of hands. And Claire, you can help me do a quick count of how many people are putting up their hands, all right? So don't be shy. You're gonna vote for one of these. I'm just forcing this, right? You're gonna vote for one of these. Who would like to vote for, go with flocculation and sedimentation? Okay, I think we got 2. Who's gonna go for filtration? 3, okay, filtration.
Everyone keeps jumping around for me.
We have an unstable student population.
8, 7?
Look, it's good enough. That's a great number. And chlorination?
4, 5, 4, 4, 5, 5.
Okay.
And
Okay.
I had 3 on the first one.
Okay. So the order that you rank them in is, for your first choice is filtration, and then chlorination was the second for first choice, and flocculation sedimentation was third for first choice. So first of all, you voted in ways that are very similar to what I would have expected. And this is why you need to take this course. So it turns out that chlorination only works if the water is clear enough that when you look at it, you don't see dirt. So that river is not it. Chlorination won't help you a bit with that river. So, okay, filtration has a very similar problem. It is going to clog so fast that it can't treat water that's this dirty. So this is like the cool insight that is not out there in popular culture. In popular culture, you think that if water is dirty, you should filter it. But what we as engineers know is that if water is dirty, the filter won't work. So if the water is dirty, the only option is flocculation and sedimentation. And then you have the luxury of adding filtration, and then you have the luxury of adding chlorination. But they have to go in that order. And doing it out of order just makes no sense. And wow, the number of people that have that one wrong is really, really, really high. And what's interesting is that has huge implications for development work, like people who are working in around the globe and who are saying, you've got a problem with your water supply, let me fix it for you. So often individuals go to filtration and chlorination when those have no chance at treating the water given how dirty it is. Wow, did I rant and rave on that a little bit? Sorry about that. Pretty intense. I'll try to back off and I'll take my meds so I don't get quite so excited, right? Okay. Wow, the effect of chlorination. So we like chlorination because it kills things. And this table gives you tons of data about how fast chlorine can kill things. And I'd like you to focus on that last column that I've highlighted, CT for PC star. So PC star, oh man, I got to define this. So you know the P function, like pH. You didn't know it was a function. P is a function. It means negative log. Okay, negative log base 10. So the P function is negative log base 10. So PC is the negative log base 10 of some concentration. And the star stands for, I've made this concentration dimensionless by dividing by the initial concentration and dividing the final concentration by the initial concentration. So all of that to say that if you have a PC star of 0, it means that you did nothing and what's coming out of your system is the same as what went in. A PC star of 1 means that you removed 90% because you're down to 0.1. A PC star of 2 means that you removed 99%. You're down to 0.01. Okay, so you would like a high PC star. That means that you're doing a great job of removing things. So to get a PC star of 1, meaning that we're removing 90% of these pathogens, for the first one, for this Campylobacter, it only takes concentration in milligrams per liter times time in minutes of 0.125 to kill 90% of them. Which means that if you had just this low concentration of 0.125 milligrams per liter for 1 minute, that would kill 90% of that Campylobacter. 0.1 milligrams per liter of chlorine is a very reasonable dose. That means that Campylobacter is easily killed by chlorinating, assuming that you can maintain a chlorine dose there for a minute. And if you look down on this slide, so what you're looking for are which are the bugs that it takes a lot of chlorine, a high CT to get a PC star of 1. And the ones that show up are, there's this Mycobacterium where it takes 17. So remember that number. And now we're going to go look at what happens if we go to, okay, we'll do this one first. Look at this. There's two cholera organisms. They're related, but they're different. They're a little bit different in how they work. And one of them is super easy to kill, so easy to kill that they didn't even bother giving the number. okay? They got 100% death rate, and so we weren't able to calculate how much chlorine it actually took to kill a few. And then the other one is super difficult to kill. So the question is, how could that possibly be? How could this one organism be so variable that one bacteria cell is super hard to kill and another one is so hard to kill? And the answer is that the one that's hard to kill, when it hangs out, it forms an aggregate of a whole bunch of bacteria. And guess what happens? The ones on the outside of that aggregate get nailed by the chlorine and they die, but the ones on the inside of that ball are protected. So that's pretty cool, but not in a way if you're trying to keep people safe. So the last conclusions, and then we're gonna jump to the gather town. If you look at viruses, their CT values are even smaller than bacteria. So it's even easier to kill viruses than it is to kill bacteria. If we go to protozoans, here's a number that is scary. Look at that number, 7,200. A huge CT, concentration times time, required to kill cryptosporidium. Basically, it means that you can't kill cryptosporidium by chlorinating and have chlorine levels that anybody will be willing to drink. So protozoans are harder to inactivate than bacteria. And then if you look at bad bugs, you'll discover that it only takes one cryptosporidium to make you sick. And that means that when we're trying to remove particles, we should be thinking about, we're trying to get that last cryptosporidium out of our water. And I think with that, I can end. You can read the summary on your own, and let's jump to Gather Town and jump into teams. I'll come around and say hi and start working really, really hard on those, on all of those